All right, let's go ahead and get started. I do want to welcome you to this worksheet. This is pH calculations. Obviously, we're going to need a calculator for this one, so if you don't have one handy, go ahead and pause the video and we will get started. So what we want to do is start with a definition. What do we mean by pH? Well, we've already looked at the scale of pH, and we said that the scale starts at 0 and goes to 14. Now, that's generally what we say, but to be honest with you, as we're going to learn in this worksheet, actually the pH can go a little bit lower than 0 and a little bit higher than 14. 7, of course, is neutral. It's right in the middle. So let's take a look at a couple of problems. So here we go, calculating the pH value. So we've looked at this equation. pH is equal to minus the log of the hydronium ion concentration. Now, it's important to note that the reason we say hydronium ion concentration is because of the fact that even though it's hydrogen ions that are determining the pH, in practice, H plus plus H2O, and we've always got H2O in the solution, obviously, is going to become H3O plus, right? So we say that H plus hydrates to form hydronium ions. So hydronium ions then are actually what is driving pH. So pH then is equal to minus the logarithm of the hydronium ion concentration. It's important to know what logarithm means. Logarithm means power. So we're looking for the power, right? The power of the hydronium ion concentration. So let's take a look at the first one. It says determine the pH for each H3O plus concentration below. So they're telling me that 1 times 10 to the minus 9 molar is the hydronium ion concentration. So remember that the formula says that pH is equal to minus the log, and I've just told you that log means power. So if I look at the power is negative 9. So a negative 9, of course, is positive 9. So we can do that one without even using a calculator, right? We can just do that in our heads. Let's look at number 2. Number 2 says 1 times 10 to the minus 2. So 1 times 10 to the minus 2, that's a hydronium ion concentration of 1 times 10 to the minus 2. So we're going to look at the power. The power is minus 2. So log means power. So the formula says pH is equal to minus the log of the hydronium ion concentration minus the power of the hydronium concentration. As long as this number is 1, you don't need a calculator. So we were able to do number 1 and number 2 without the use of a calculator, because 1 times 10 to the minus 2 has the power negative 2. Negative and negative 2 becomes 2. All right? All right, that's pretty simple so far. Let's take a look at number 3. We have 6.75 times 10 to the minus 2. Well, this time we're not going to be able to do this in our head. In other words, it's not a simple matter of looking at the power and determining from that power what the pH is. What we're going to have to do is we're going to have to use a calculator. So we're simply going to plug in. We're going to say minus the logarithm of this number, 6.75 times 10 to the negative 2. So we'll just plug it in just like that. Find the negative sign. It's usually be in parentheses in the lower part of the calculator. LOG, make sure it's LOG and not LN. We want the base to be 10, not E. And then 6.75, second EE, negative 2 will give us this times 10 to the minus 2 part. When we do that, we'll hit the enter button and we get this number 1.171. I want to talk just a little bit of significant digits at this point, and that is to say this. There's a special rule for significant digits of logarithms, and that is you're going to look at the total number of significant digits in this part of the number. 6.75 obviously has 3 significant digits. What that allows me to do is have 3 numbers to the right of the decimal. Now, it looks like in 1.171 there are 4 significant digits, but in fact, the significant digits happen after the decimal for logarithms, or in this case, pH. So we're going to report our pH as 1.171 because we want 3 numbers to the right of the decimal, because we've got 3 numbers in this part of the molarity. So let's look at number 4 now. We've got 1.8 times 10 to the minus 13. Another one we're going to have to use a calculator on because of the fact that it's not 1 times 10 to the minus 13, but 1.8 times 10 to the minus 13. So here we go. We're going to say minus the log, minus the logarithm, log, not ln, of this number, 1.8 times 10 to the minus 13, and We'll hit the equal button, and we get this number, 12.74. Again, two numbers, two significant digits here. So we want two numbers to the right of the decimal. We're going to say 12.74 is our final answer. That's our pH. All right, let's take a look at the next one. It says calculate the H3O plus concentration for the given pH values below. So this time we're going to go the opposite way. So they tell me that the hydrogen ion concentration is 11.0. The hydronium ion concentration, I should say, is 11.0. I could simply disregard the mathematics and just say, well, that's the power. So my hydronium ion concentration would be 1 times 10 to the minus 11. But I'll set it up mathematically. We have 11.0 is equal to minus the log of the hydronium ion concentration. I'm going to pull the negative side to the other side. Now, negative 11 is equal to log of hydronium ion concentration. And then what I'm going to do is exponentiate. I'm going to push both sides to the power of 10, up to the power of 10, or rather, make 10 the base and make these things their powers. So 10 to the minus 11 is equal to 10 times 10 to the log of the hydronium ion concentration. Notice that 10 to the log of something is that thing, so that gives me the hydronium ion concentration. And so my answer would be 1 times 10 to the minus 11. Likewise, for number 6, we've got 7.94 times 10 to the minus 5 because of the fact that our original pH was 4.1. This is for tomatoes, by the way. So we say 4.1 is equal to minus the log of the hydronium ion concentration. Pull the negative over to the left, and we've got negative 4.1 times 10. Negative 4.1 is equal to the log of the hydronium ion concentration. Exponentiate at this step right here. We get 10 to the minus 4.1 is equal to 10 to the log of the hydronium ion concentration, and then solve that. By the way, we're going to use the second button on this one. So we're going to hit second log to get 10 to the negative 4.1. We'll hit the equal button. We get 7.94 times 10 to the minus 5. Number 7. Notice this time we've got a negative pH. It can happen. It's not very common, but it can happen. So we got a negative pH. We say negative 0.32 is equal to negative the log of the hydronium ion concentration. We'll pull the negative to the other side. We get 0.32 is equal to the log of the hydronium ion concentration, and 10 to the 0.32 is equal to 10 to the log. We'll exponentiate in this step right here. That gives us 2.09 as the hydronium ion concentration, and we're done with 5, 6, and 7. Let's go to the next one. We're going to learn a couple of new rules here. This time we say in the same way that pH is equal to minus the log of the hydronium ion concentration, pOH is equal to minus the log of the hydroxide concentration. pOH is equal to minus the log of the hydroxide concentration. So there's another new rule that we're learning. pH plus pOH is equal to 14, so the sum of the pH and the pOH is 14. And the hydronium ion concentration and the hydroxide ion concentration multiplied together gives us this value. It's called Kw, and it is 1 times 10 to the minus 14. So if I know one, I can easily determine the other. Let's take a look at number 8. Number 8 says determine the missing information. So in this case, they give me the 7. So if I know that the pH is 7, the pOH must be 7 as well, because 7 plus 7 is 14. So that gives me this number right here. Now, I know that pOH is equal to minus the log of the hydroxide ion concentration. So if the pOH is 7, the hydroxide ion concentration must be 1 times 10 to the minus 7. These two values, the H3O plus concentration and the hydroxide ion concentration, have to multiply together to give me 1 times 10 to the minus 14. Therefore, this one also has to be 1 times 10 to the minus 7. When the pH is 7, that is neutral, and that gives me this box right here. Second row, we've got 3.5 times 10 to the minus 12 is equal to the molarity is equal to the hydroxide ion concentration. If that is true, then we're going to say that this value times this value is equal to 1 times 10 to the minus 14. Or another way to say that is 1 times 10 to the minus 14 divided by 3.5 times 10 to the minus 12 gives us what? When we do that calculation, we get 2.9 times 10 to the minus 3, and that gives us this value right here. All right, how do we determine the pH? Well, if we know the hydronium ion concentration, we can use pH is equal to minus the log of the hydronium ion concentration. So if we know this value, we can get this value. Or alternatively, we could do this. If we know the hydroxide ion concentration, using pH is equal to minus the log of the hydroxide ion concentration, we can get this value. Nonetheless, these two values have to add up to 14. So either way you want to do that, it's fine. Nonetheless, 2.54 plus 11.46 have to add up to 14, and they do. The pH is equal to 2.54. That's less than 7, so we are dealing with an acid on this second row. Let's look at number 8. Number 8 is 3.98 times 10, excuse me, pOH is 2.6. So this value, or 14 minus this value, is this value. So we've got 14 minus 2.6 is 11.4. So now we've got the pH and the pOH to find the hydronium ion concentration, the hydroxide ion concentration. It's a simple matter of using pH is equal to minus the log of the hydronium ion concentration to get this value. And so I determined it to be 3.98 times 10 to the minus 12. And then pOH is equal to minus the log of the hydroxide ion concentration. I've determined that to be 2.5 times 1 times 10 to the minus 3. Remember that this number and this number must add up, or excuse me, this number and this number must multiply together to give me 1 times 10 to the minus 14, and they do. Remember that if I have a pH above 7, and I do, it's 11.4, then I'm dealing with a base, and that is it for number 8. All right, I'm going to pause right here just for a second. You can stop the video if you'd like. This is the mathematics that I did to produce those squares in this table. So I'll pause just a moment if you want to peruse that, and if you want to pause the video, you can do that as well. All right, let's move on. All right, next question. It says acid-base indicators are compounds whose colors vary with pH. At each given pH, state the indicator's color. So they're giving me the hydronium ion concentration. From that, I can use pH is equal to minus the log of the hydronium is equal to give me the pH, and I do that, and I get 12.1. So that gives me a pH of 12.1. Remember that litmus turns red litmus, basic solutions turn red litmus paper blue, so that means that litmus would turn blue, and phenolphthalein is another indicator that's pink when it's basic. So we're dealing with a basic solution here because 12.1 is above 7, and that'll do it for that line. The next one is a pure substance because actually it's a neutral pH. 10 to the minus 7 molar gives me a pH of 7, obviously. Don't even need a calculator for that one. I'm sorry, I skipped the second row. So let's go ahead and go to that second row there, 4.52. From pH is equal to minus the log of the hydrogen ion concentration or hydronium ion concentration. I get the hydronium ion concentration to be 3.02 times 10 to the minus 5. So that takes care of that little square right there. And then obviously 4.52 is less than 7, so this is going to cause blue litmus paper to turn red, phenolphthalein to be clear, and again it is an acid. All right, now the last line would be this. Again, we've got 10 to the minus 7, so the pH would be 7. Remember, because it's neutral, it's not going to turn litmus either red or blue, red litmus paper blue or blue litmus paper red. It's just going to look wet, so I wrote wet right there. Phenolphthalein would actually be a very, very light pink, barely detectable at 10 to the minus 7. Remember, we're at the equivalence point, so the hydrogen ion concentration and the hydroxide ion concentration are essentially the same. So it'd be, if it's pink at all, it would be a light pink. So we put light pink right there for that scale. It is neither acidic nor basic, rather it is neutral. So I put neutral just right there. All right, that'll do it for number 9. That'll do it for this worksheet. And hopefully we understand the relationship between pH and pOH, the relationship between pH and the hydronium ion concentration, pOH and the hydronium ion concentration. And all right, that'll do it for this one. Thanks. Bye-bye.